first objective. We should be able to describe chance behavior with a probability model, define and apply basic probability rules. 3, determine probabilities from two-way tables. I know you guys like those so much, kind of like the conditional distributions. And then 4, construct Venn diagrams and determine probabilities with Venn diagrams. And we'll hang out with Venn diagrams quite a bit because those appear in many different places. Probability models, description of chance behavior contains 2 parts. You have the sample space and you have the probability model. Sample space is the set of all possible outcomes. Your sample space is your set of all possible outcomes. And a probability model has 2 parts to it. A probability model consists of a sample space, and it also consists of a probability for each outcome. Give a probability model for the chance process of rolling 2 fair 6-sided dice. What's it mean by a fair dice? It's not weighted, it's not loaded, and if it was a weighted or loaded dice, it means like if you like go to a casino, if they have a weighted dice that they're using, it might be like they take one of the dots on it and they drill it out, and in place of it they put like a metal slug or something so that it's weighted in that way that one is going to land down more frequently. So that's what a weighted dice would be, but we talk about fair dice in here. So we have 1 red dice, 1 green dice. That's not what those colors look like, but we roll them both, and here's all the possible outcomes. If I roll a red dice, I could get a 1, and with that, I could roll a green dice, and I could also get a 1. Or with my red dice, I could get a 1, and the green dice could be a 2. I could get a 1 and a 3, a 1 and 4, and there's all your possible outcomes. So to talk about our sample space, how many outcomes do we possibly have? There's 36 different outcomes. We've got 6 this way, we've got 6 across the top. 6 times 6 is 36 possible outcomes. So that's your sample space. There's 36 outcomes. Since the dice are fair, each outcome is equally likely. Since the dice are fair, each outcome is equally likely, and each outcome has a probability of, say I look at this one, what's the probability I get a red 6 and a green 1? The probability I have that occurring is 1 out of 36 total. Here's a side example to kind of go along with this and just follow up one more time. Imagine flipping a fair coin 3 times. Give a probability model for this chance process. So probability model, it's got 2 parts. What's your sample space? What's the probability of each outcome? So our sample space, what's it look like? Detail it out. You flip a coin 3 times. The first time it could be a heads, second time it could be a heads, and the third time it could be another heads. Right? Well, list them all out. You could go heads, heads, and heads. We could get tails, tails, and tails. We could get heads, heads, and then a tails. Heads, tails, and then a heads. And then tails, heads, and heads. And what else? 2 T's and an H. A T, an H, and then a T. The order does matter, because it's like the first time I flip a heads, then I flip another heads, and then I flip a tails. Well, here I flip tails, and then I flip a heads, and then I flip another heads. And last but not least, what's my other option here? Do you kind of see what I did? Here's what I did to kind of keep a logical process to it. If I move it up, you guys could see. I had all my tails, I had all my heads. Then I'm like 2 tails, I put the H on the end, I put the H in the middle, and I put the H first. Here I put the tails on the end, tails in the middle, and then tails first, just to kind of keep it logical for me. So my sample space, this is what my sample space looks like. How many outcomes are there? The sample space has 8 outcomes. And then the probability of each outcome, the probability each of these happens would be 1 out of 8. So this would be like our sample space, this would be our probability. Write it again. An event is any collection of outcomes. Any collection of outcomes from some chance process. An event is a subset of a sample space, usually designated by capital letters like A, B, C, and so on. If A is an event, we write its probability as like P of A, probability of A. And here's an example of an event. And in the dice rolling example, suppose we define event A as sum is 5. So we're looking at the smaller subset of all these possible outcomes. How often or how many different ways can we get a sum of 5? We could get a 1 and a 4 add up to 5, a 2 and a 3, a 3 and a 2, and a 4 and a 1. Those are all the ones that would add up to 5, those sets of dice. So if we say probability of A, that's like saying the probability that the sum is 5. Probability of A, probability the sum is 5 is what? I have 1, 2, 3, 4, 4 outcomes out of the 36 total. And for my sake, I know every single time it's like simplify your fractions, simplify your fractions, simplify your fractions. So we're just going to leave it like this. You don't even need to divide it out and get a percent for me. The probability of getting sum of 5, you could figure out that percentage, but just leave it as 4 out of 36. Okay? So suppose B is defined as sum is not 5. What's the probability of B? If the sum is not 5, this is the times that it is 5. So what's the probability that it's not 5? 32 out of 36. So we think about that and we're like, oh, we know that's 32 out of 36. But in reality, what are you doing? We're doing 1 minus 4 out of 36, right? It's like, we could even say 36 out of 36 minus that 4 out of 36 gives us 32 out of 36, right? Okay, that's important because we're going to come back to that in a little bit here. So when we talk about probability, there's a ton of different rules that we have to follow. A ton of basic rules. First of all, you guys know this, the probability of any event is the number between 0 and 1. And often, you'll see it written like this too. The probability of A, probability of event is a number between 0 and 1. That's just like the shorthand for it. All possible outcomes together must have probabilities whose sum is 1. You take all the probabilities in a model and you add them up, they all have to add up to 1, because it's like out of 100%. If all outcomes in the sample space are equally likely, the probability event A occurs can be found using this formula. It's the number of outcomes corresponding to event A out of the total number of outcomes in the sample space. Probability an event does not occur is 1 minus the probability that it does occur. Finding the probability it does not occur is 1 minus the probability that it does occur. And this has a special name for it. This is called the complement rule. They like complement each other. The probability it doesn't occur, the probability it does occur, those add up to 1. And it looks like this. Probability of A to the C. It's like saying the complement of A, the probability A does not occur, equals 1 minus the probability that A does occur. If two events have no outcomes in common, probability that one or the other occurs is the sum of their individual probabilities. And if two events have no outcomes in common, the probability that one or the other occurs is the sum of those two probabilities together. You add those two probabilities together. And this is called the addition rule for mutually exclusive events. The addition rule for mutually exclusive events says probability of A or B equals probability of A plus probability of B. We're gonna, these are properties, and we're gonna work with these throughout the rest of chapter 5. So I don't expect you to know it all and have it all memorized right now at this point. It's just something to refer back to. Mutually exclusive or disjoint. If they're mutually exclusive or disjoint, that just means they can't occur together. It's two events that have no outcomes in common. Two events that have no outcomes in common, they can never occur together. What's a real life example? Mutually exclusive. If I find the probability of somebody's GPA, can they be in a 3.0 to 3.5 range as well as 1.0 to 1.5? Those are mutually exclusive events. You can't have a probability in both categories. You might look at an example and you might say, what's the probability somebody's female and they have brown eyes? You can be in both of those categories. You can be female and you can have brown eyes. Distance learning courses are rapidly growing in popularity among college students. Randomly select an undergraduate student who is taking distance learning courses for credit and record the student's age. Here's the probability model. So what's the probability somebody's taking a long distance learning course? They can't be in this age range as well as that age range. That means they're mutually exclusive. Those can't occur together. So to show this is a legitimate probability model means they all have to add up to 1. Do all those probabilities add up to 1? Try it. 0.57 plus 0.17. So they add up to 1, and all probabilities are between 0 and 1. So there's two conditions. Do they add up to 1, and are the numbers between 0 and 1? You can't have negative probabilities because, first of all, it doesn't make sense. But that just kind of reinforces they have to be between 0 and 1. Find the probability that the chosen student is not in the traditional age group 18 to 23. So if I say probability of not 18 to 23 years old, what does that mean? When we put in a not there, that's like saying the complement. If they're not in this one, that means we go 1 minus the probability that they are. If they're not in that age group, it's 1 minus the probability that they are. And that gives us 0.43. Some of you are like, well, Ms. Ruth, can't I just look at that? If they're not in that age group, that means I add these three numbers together? Yeah, exactly. That works too. There's two different ways to do it. Sweet? You guys try the last two on that page. And then I'll put the answers up here. You can check, and I'll put your assignment up in a second.